Alright, let's start our second video from the float pointing standard of IEEE. So in the first video, have just take a look on some basic principles and some historical facts. Now we are going to be a bit deeper on the computational representation of numbers. It's necessary to represent positive and negative numbers. The simplest idea is to represent the number with two parts, signal and module. In this case, 1 bit is used for the signal and 31 bits for store the number module. However, the most common method is complement of 2. Let x be such that 0 is lower than x is lower than 2 to 31 minus 1 is represented in its binary form. Already the negative value minus y such that minus 1 is lower than y is lower than 2 to 31 is stored in the binary representation of the positive integer. So if you do like that, you are going to make the complement of 2 of this number. Computational representation of numbers. On a 32-bit system, if two positive numbers are added and the result is greater than 2 to 31 minus 1, the so-called integer overflows occurs. Subtraction of two integers representing the representation of add-on 2 does not require additional hardware. So this is an important topic because you can make use of very basic hardware such as some basic orders to make subtraction. This is very useful, by the way. Computational representation of numbers. Rational numbers can be represented by pairs of integers, one numerator and a denominator. This representation is accurate, but it's convenient from an arithmetic point of view. Systems that represent rational numbers in this way have been called symbolic. For most cases, the actual numbers, however, are stored to use binary representation. There are two methods, fixed point and float point. Fixed point, 1 bit for the signal, a group of bits for representing the number before the binary point, and a group of bits to represent the number after the binary point. So in this example, I'm going to show 11 divided by 2. So this is a positive number, so you have here the 0 to represent the number. A group of bits to represent the whole part, 5. So you have here 1, 0, 1. So as you can see, 1 times 2, 2, 2. So it is 4 plus 1 is 5. And here you have dot 5. So here's 2 minus 1, right? So this is a way to represent fixed numbers. This range, of course, approximately 2 minus 16 to 2 to 15. The fixed point is quite limited as to range that can be stored. It's currently under use for numerical computing. However, fixed points in microcontrollers are more economical, have simple internal circuits, and require less memory. As you could see in other videos, we also made use in our research group to fixed point to make fast and very efficient Poisson random number generators. Computational representation of numbers, such as float point, is based on explanation, notation, or scientific. A number x is represented by x equals plus or minus s times 10 to e, in what 1 lower s is lower 10, where e is an integer. The number s and e are called significant and mantissa and exponent, respectively. The exponential representation of this, so the first step to make an exponential representation is to put the dot after the just integer different from 0. The decimal point points to the position immediately after the first non-zero digit. This is the reason for the floating point name. On the computer, base 2 is used. Thus, x is written as. So in the binary, you have the same equation here, but in this situation, what you're going home here, you have 1 louder than S, louder than 2. Computational representation of numbers. The binary explanation of the signifier is, so B0, B1, B2, B3, then B0 equals 1. The number 11 divided by 2 is represented as, so here is the way that we are going to represent this number. The bits of the binary dot are called the fractional part of meaning. The equation 1 and the 2 are representation normalized of x, and the process of obtaining this representation is called normalization. To represent a normalized number, its binary representation is divided into 3 parts: signal, exponent e, and significant s, in that order. So example 5. If you have, for example, to represent some systems with 32 bits, so you can use 1 bit for sign, you can use 8 bits for exponent, so it can go from -1 to 8 to 1 to 7. S use 23 bits to store the value of the period. It's not necessary to store B0. It's called hidden bit because it's always going to be 1. If X belongs to R, can be stored exactly on a computer, then X is called number floating point. Otherwise, X must be rounded. The number 71 is represented by. So look, it's really important to realize that even a just integer number here, like 71, when it's going to represent in a computer, it looks like a decimal number. That's why when you're going to represent a big number, you can lose some information, right? So in this way, you are going to represent 0, 6 bits for, you have to represent as an exponent here, as you are going to represent in the next slides, and the 71, you can use here the 3 zeros and the 3 ones, and you complete all the remaining space for zeros here. E-bits represents the conversion of 6 to the binary number in the exponent. If X number does not have a finite binary expansion, it's necessary to finish this expansion. This process is called truncation. Consider the number 1 divided by 10, whose expansion is 1 divided by 10 is like that. So this is the answer, as you can see, of previous exercise. But this expansion, it's not finite. It's going on forever. So first of all, we have to truncate. First we must normalize and then truncate. So the 1 divided by 10 representation in a floating point is 0 for the sign. You have to use here 4 bit, you have to represent -4 because you have to use here, look, now you have to go the right with the dot 4 places here, so you have to represent -4, and after that you don't need to represent the height number, this one number 1 here, and you are going to represent 1 0 0 1 0 0 and so on and so forth, right? A precision P of a floating point system is the number of bits of the signifier, including the hidden bit. In the 32-bit system, P equals to 24, with 23 bits being the signifier and 1 hidden bit. A normalized floating point with precision P is expressed by equation 3. So in this way, you have see here the representation numbers times 2e. The smallest floating point x that is greater than 1 is just like, because this is the representation of P here, so it's the smallest number. A special name, machine epsilon, is given, epsilon of the machine, to the distance between this number and the number 1. So the epsilon of floating point representation is the value of 2 elevated to minus P minus 1. So if you have, for example, P here equals to 24, you are going to have 2 elevated to minus 23. More generally, for a float point x given by 3, we define ULP such as, so the ULP is the epsilon machine times 2 to e, so e is the exponent used for representing that number. ULP is the short for unit in the last place, from the last position. If x is greater than 0, then ULP x is the distance between x and the next largest point bigger. If x is lower than 0, then ULP x is the distance between x and the next smallest floating point. So far, only non-zero numbers have been discussed. 0 cannot be represented using the hidden bit, so because you are going to have just zeros, of course. Until 1975, this issue was solved by not using the hidden bit. The IEEE standard reduced the exponent by 1 and used a special character to identify the 0. Consider the following fictional binary system in which all numbers can be represented as values. So this is a sort of toy representation here, just with three bits for the mantissa, and the exponent are going to represent just by minus 1, 0, and 1. The set of numbers represented can be seen just in this following figure. This figure has been adapted from the book of Erivelton. It's quite useful to see. What's going on here? If you have just 3 bits, B01, B02, and the exponent can be seen just minus 1 and 0 and 1, you can have just these numbers represented in this line. The 0, and after that you can represent it minus 1, minus 2, minus 3. But an important issue here is that the space between the numbers become bigger and bigger, right? So as you can see here, look, the representation of the number are bigger and bigger, but the distance between 0 and the first positive number greater than 0 is bigger than all the space here, right? So this is really tricky. We are going to see it as the sub-number numbers, and it's quite tricky and it's not so investigated, in my opinion, in many research areas. The procedure of equation 6 is p equals 3. The largest number is 1.11, and it's equivalent to 3.5 in 10 base. The smallest positive number is 1, is equivalent to 0.5 number 10. The float point after number 1 is 1.5, so the epsilon of machine is 0.25. The distance between each number is the ULP. So the distance between 0 and plus or less or negative 0.5 is greater than distance between 0.5 and plus 1. This distance can be reduced with the introduction of subnormalized numbers. Von Neumann was initially against the floating point. It's possible to choose microprocessors with fixed or float point to represent such numbers. Float point has been used since the mid-1950s. During the next 2 decades, each company adopted a different standard. IBM, a market leader during the 60s and 70s, adopted a 24-bit hexadecimal IBM 360 and 370 standard. The mantissa was stored in 24 bits to be interpreted as 6 hexadecimal digits. 1 digit was for the sign, 7 for the exponent, and 16 for the power of 16. Normalization was mandatory only for the fixed hexadecimal digit, which should be 0. As a result, some numbers were less accurate than others, which is really, really odd. IEEE representation. So now we are going to start, finally, the representation that is most important. In a collaboration between researchers and designers of microprocessors, a standard for float point representation and arithmetic was developed in the 70s and the 80s. The group of scientists and engineers was led by the Institute of Electrical Engineering and Electronic Engineers, IEEE. The group became known as IEEE P754. The scientific community was led by Yuri Khan. So this is a professor of University of California at Berkeley. The industrial participants were in those age Apple, Digital Equipment Corporation, Intel, HP, Motorola, and National Semiconductor. Cannon received the Alan Turing Award in 1989 from ACM. The founder of MATLAB, Clive Moore, even mentioned that the two major tourist attractions in the United States were the Grand Canyon and the meetings of IEEE P754. Of course, this is a statement in a very American style, but you can see it's exaggeration, but of course it was very important for development of the science in the whole wide world. The IEEE stands for Binary Floating Point, and Arithmetic was published in 1955, being officially called this number here. In 1989, it received international recognition as IEC 559. In 2008, an updated version was published, being called IEEE 75 2008. In 2011, the international standard was approved to use. And now in 2008-9, there are some small updates. So there's a new version of this standard that you are not going to see because the changes are not so expressive, but it's worth to take a look. IEEE 75 standard address the following topics: formats for arithmetic, formats for data exchange, rules for rounding, arithmetic operations, and exception handling. The IEEE standard has three essential aspects: consistent representation on all machines that adopt the standard, round operation suitable for the floating point, consistent handling of exceptions, such as division by zero. The first digit of IEEE standard is hidden. This requires a special representation for the zero. Another special representation required is the number infinity. There is also need for special representation for 0, minus infinity. As you can see, it's not so well known, but in a computer you have positive and negative 0. There is also the NaN symbol, which represents not a number, right? This is an important footnote here. Walter Wood does not consider infinity as a number. It treats it as a symbol that is only part of the set of extended reals. Okay. The IEEE standard specifies two basic formats, single and double. The single format uses 32 bits. It's represented here in the figure 32. So you have the sign, 8 bits for the exponent, and 23 bits for the mantissa, or for the significant. So the zeros represent like that, so in 10 base, and we are going to represent here, you are going to use such that, look, you are going to use 0 as the bit, the height bit here, and minus 126 here. So this is different, of course, in this situation here, right? Okay, let's go on. The signal format has 1 bit signal, 8 bits exponent, 24 bits significant. The sign represents the numbers. The first line represents the sign, the significant, the exponent and the significant. All lines except 0 starts with a height bit 1. The exponent use a displaced representation, Bayes representation. The exponent is the binary representation of e plus 127. So the number 1 in base 10 is represented like that. So in normalized, so we have 0 here. But as you have to represent with addition of 107, we are going to represent 0, the exponent, which will represent 107, and all the zeros here. All right, so as you can see, this representation is very, very useful. So you can have a lot of explanations and a lot of information, and very many details that you are going to see some of them here. The range of E ranges from binary number 1 to 254, which corresponds to minus 106, and the maximum number of exponent is 107. The smallest positive normalized number is, so we have 0, the exponent, and all zeros here in the mantissa. This value is denoted as like that: 2 to minus 106 is around 1.2 times 10 to minus 38. The largest normalized positive number is 0, the exponent, and here. You can see here there is not the one here because it's devoted to infinity. This value is denoted by n max, so you are going to see here. So this is all the number, and the biggest number, as you can see here, is 3.4 times 10 to 38. Subnormalized numbers are the combination of zero exponent and no zero fraction part. Subnormal numbers cannot be normalized, as normalization would result in exponent outside the representation range. Subnormal numbers have their precision reduced as the number decreases. So as you can see here, so the number 2 minus 107 is represented like that. So what is going on here? You cannot represent minus 107. So instead of use that, you are going to represent 0.1 times 200. As you can see, in such a way, you are going to put 1 here, but you can reduce the places to represent the number, the decimal parts, right? IEEE representation. In format double, this represents here all the numbers. So this is a table that you can see here just to take a look, because this is all the numbers. So you don't need to realize, but this is very useful just to have a look, right? The precision P24 corresponds to approximately 7 decimal digits, or equivalent to 24. The representation in IEEE single format, pi, is represented like that, is when converted to decimal part 3.4. So this is just to see what is going on in this sort of representation. Now you are going to have a look in rounding. Numbers in IEEE standard can be expressed in the form like that, where P is accuracy for normalized numbers, P0 equals to 1. So the exponent goes from E minimum and N maximum. For subnormalized numbers in 0, you have like that. So Ex belongs to R is the normalized range. The number 0 and the infinity and subnormal numbers are not in the normalized range, although they are valid numbers. If the real number is not a floating number, then at least one of the following situations occurs. X is out of the number range. For example, X, this number here, 2, elevated to 130, is outside the normal range, so in the format single. The X binary expression requires a number greater than P bits for exact specification. So for example, if we are going to represent 1 plus 2 to minus 25, as you can see here, it's going to be necessary more digital place to represent in a single format, so it's not possible. This requires more bits than the single format allows. In both cases, it's necessary to approximate X by a different representation of the original real number, right? So, in this situation, you cannot use the precise number. So what's going on in this situation? Let the number x minus be the floating number closest to x, which is less than or equal to x. Let x plus be the floating number close to x, which is greater than or equal to x. If the nearest number is 0, the sign of 0 would be the sign of x. Let x represent pair. X, this is the equation 10 here, so this is just the number. The closed floating number that is less than or equal to x is 10. So as you can see here, it's possible to realize these numbers. The difference, it's going to be just more more bits to represent. X minus is obtained by truncation of the binary expression of Matisse, in which BP plus 1 are discarded. If x is not a floating number, then x plus, if you put like that, you are going to put just the ULP here, so you are going to reproduce this distance. So the range between x minus and x plus is this equation 13. The value of 13 is equal to ULP of x minus. So there are some special functions in MATLAB and Octave that you can have a look. In your online meet, I'm going to show that. If x is greater than n max, then x minus equal n max, and x plus is plus infinity. If x is positive but less than n minimum, then x minus is a subnormal or 0, and x plus is subnormal or n min. If x is negative, the situation is the contrary. The IEEE standard defines the correct round value of x denoted by round x as follows. If x is a floating number, then round of x equal x. Otherwise, the value depends on rounding mode. There are some couple of different ways to round a number. Round down, round x is equal to x minus. Rounding up, round x is equal to x plus. Round towards 0, so this is equals x minus if x is a positive number, and x plus if it's the negative. Rounded to the nearest is the most useful number, is either x minus or x plus, depending which is the closest to x. If there is a tie, that with less significant bit equal to 0 is chosen. The default mode in virtually all applications is rounded to nearest. So this example, we use the IEEE single standard work out an example x minus and x plus are the same distance as x. So this is to see, for example, how it's impossible. Let x be a real number. It's defined as absolute round error. So the equation 4 represents the distance between the real number x and its representational computer. The absolute round error is less than the interval between x minus and x plus. So the absolute number is lower than the ULP. With the rounded to nearest, we have, instead of pi minus 1, you have minus p. So it's half of the ULP. Definition 4. The relative rounding error is the same that absolute, but you use the division by x here, so it's almost the same. You are going to see by equation here, that's this manipulation, it gives epsilon. For round to the nearest number, we have epsilon divided by 2. The number of bits in agreement for rounding to the nearest is log 2 of the relative error, so it's greater than p, right? So this is quite important, because this is the unique theorem of the book, and the number of decimal digits is greater than here. And for the single format, round x and x agree at least with 7 digital halves. net table 2. Let X belongs to R be normalized in binary floating point system with P accuracy. So if you do like that, you can express the X as X multiplied by 1 by plus delta. And for a delta that satisfies this inequation here. Or for round mode for nearest, it's the same, but delta is lower than a half of epsilon. In a central point of the IEEE standard is to require that arithmetic operation round correctly, addition, subtraction, multiplication. Rest operation is square root correctly rounded. Correct and round format conversion. Round correct means rounding up will tailor the target result. It's common for the result of a two-point arithmetic operation floating point is not a floating point. So, for example, 1 and 2 minus 3 are floating pointing, exactly the representation. But if you are going to add these numbers, it's not a floating point. So think about that, and if you have doubts, please ask in our online meeting. Now it's very important, this slide is very important for some computer simulation. Let X and Y floating numbers. So then, if you are going to try to use X plus Y, X minus Y, X multiplied times Y, X divided by Y. So you are going to use, in fact, the round operation. The result is not going the same result. You have to be in mind that you can get an error. And this error is represented by a multiplication by delta, and where delta is lower than half of epsilon of the machine. So this exercise 4, I'm going to ask you to make the calculation, use the octave language. So if you use x equals z equals 1 and y equals 2 elevated to minus 25. So in the letter A, you are going to calculate x plus y minus z in a format single. In XB, you are going to do the same, but in a double format. See the difference? Make some conclusions and put in a small report with your team. Availability of round up and down models allows the programmer to do any computation twice, each time of the modes. The two results define an interval in which the result exact must be contained. This methodology gives rise to interval computing. This is another course. Of course, this could be a completely different course, interval computing. It's a topic of my research as well. It's quite important, and you can do very, very interesting things. Use this course here, right? Okay, so we are going to, with this slide, to approach the end of this second video of the IEEE floating point. I hope that you have enjoyed. If you have any questions, please ask me by mail or in online meeting. Thank you very much for your attention